The capacitor equation. The capacitor equation is the current voltage relation for capacitors that show the connection between VC and IC it is similar to Ohm's law for resistors. Because of this, sometimes you'll hear me say that this is Ohm's law for capacitors. Starting with the capacitance equation, one can easily derive the capacitor equation. Where capacitance is assumed to be a constant. So I have that Q of t is going to equal to C VC of t. But now if I take the derivative of both sides, we see here that that automatically gives me the current of the capacitor, which then should be C dV of t dt. This is the capacitor equation. Now note that this is Carlos's language. Just to be clear. So here we go. Now what I want to do is go through the interpretation of this capacitor equation. So let's look at that. The RC behavior is well studied in physics 4B. The exponential behavior of VC of t is clearly not linear, since its slope constantly changes. And we're going to show this with the curve below. But the thing to remember here is the slope of the VC of t versus t curve is proportional to the capacitor current IC of t. Right? IC of t, the capacitor equation, shows this, that now the slope, which is dc dt, is proportional to IC of t. So now what we want to look at is that we want to look at the curves for charging and discharging capacitors. So I want to plot both of these right next to each other. So we're gonna plot both the charging and discharging curves next to each other, since their slopes imply the same behavior. So on the left side, let's talk about a charging capacitor. And on the right, I'm going to have a discharging capacitor. And the thing to really remember is about the slopes of these guys. So let's start drawing these. So I'm going to go, let's assume that these are my curves. Then if I copy and paste the same curve, so I want to make sure that they're the same size. So on this axis, we're going to plot VC of t on both of them. And of course, we have our time axis here. So what we want to show is that if I have exponential behavior, it's going to look something like this for the charging. But then I'm going to have decaying like this on this axis. So in each of these situations, we're seeing that this curve represents charging of the capacitor. That means that the capacitor voltage is increasing over time, not linear. And then here we're seeing the discharging of the capacitor. So in each of these situations, I'm saying that this is the source voltage is the same as the capacitor. And at this point, the source and the capacitor are at the same value here. So the key here is the slope. So when I look at the slope, you can see that the slopes here in the beginning here are very steep. In each of these situations, I have a very steep slope. So what does that mean? Well, there's a rapid increase. Over here, there's a rapid decrease. And I'm only looking at the slope. So this immediately tells me that this is a large charging current This one is telling me that this is a large discharging current. So if I was to write that down, I would say the increase slash decrease of the current is greatest at the beginning since it represents the largest potential difference between the source and capacitor. Therefore, the current flow is highest here. In other words, we get a large current, which tells us then that IC of T is largest because the difference in the capacitor, voltage that is, has a large difference. So there's a big change. Now let's look at the other situation. The other situation, if I look at over here, you can see that as I get near the end, the slope is smaller. So this is a slow increase. This is a slow decrease as well. That tells us that we have a small charging current. And here, this tells us that this is a small discharging current. So now we can summarize the same type of analysis that we did before. The potential difference between the source and capacitor is decreasing. Therefore, there is less current flow. In other words, we have a small current, which implies a small IC, because the push, the potential difference, is a small difference.